Alright, so what we're going to talk about today here is worked examples of mechanisms. So let's take a look at the first one. This is a lever. Now we're going to assume for these first three problems ideal mechanical advantage. That means that it's 100% efficient. There's no friction. Okay? So when you have ideal mechanical advantage, the ratio of your effort to the force that you're lifting, or the force of the load, should be the same as the ratio of the distance of the effort to the distance of the load. So in this example, John wants to create a lever with a mechanical advantage of 2. If he applies this force of 25 newtons to the end of the lever, how far must he apply the effort from the fulcrum? So here's a box, the load, and it is 50 newtons is the force, and the distance is 2 meters away. Okay. Now the effort that's applied is 25 newtons. So if we want to look at the mechanical advantage is 2 to 1. Right. So he's lifting twice the load of the effort. So that means that if the ideal mechanical advantage is equal to the velocity ratio, then the velocity ratio should also be 2. So that means that your effort must be 2 times further away than the load from the fulcrum. So here's our effort. So the effort distance must be twice what the distance is for the load. Okay, so if we look down here, ideal mechanical advantage is equal to velocity ratio. We worked out that our ideal mechanical advantage is 2 because the force of the load is 50 newtons, the force of the effort is 25 newtons. Okay, so velocity ratio is equal to the distance of the effort over the distance of the load, which must be equal to 2 in the end. Okay, so 2 is equal to the distance of the effort over the distance of the load. And if we put this over on this side, we get 2 meters times 2 is equal to 4 meters. So the distance away from the fulcrum for the effort must be 4 meters. Let's have a look at the next example. Greg wants to set up a lever shown to help him lift box A by pushing down at point C. If B is located 50 centimeters from A and 150 from C, what is the ideal mechanical advantage of the lever? So this is a different type of lever, okay? So if we look, here's our fulcrum. So the distance of the load is from here to here, and the distance from the effort is from here to here, okay? So in this equation, we're not given distances, but we know that we know the mechanical advantage. We know the velocity ratio, right? And that is 150. That's for the effort divided by 50 for the load. So that means it's a velocity ratio of approximately 3. Okay. So if 3 is our ratio, and so that's all that this question is asking. Actually, it's just asking us what is the ability, what's the ratio of mechanical advantage. So this lever, because the effort's 3 times further than the load, it just allows you to lift something 3 times heavier. That's basically what it's saying. Let's take a look at our last example. Okay. Mike applies an effort of 350 newtons to the end of the lever to lift a box weighing 190 kilograms. Design a class 1 lever to raise the load. Alrighty. So we need to design a lever that can apply a 350 newton effort to raise a 190 kilogram load. Now the first thing you must realize is that kilograms is not a force. Okay, we have to convert kilograms to newtons, so it's like this one. So the way that you do that is force is equal to mass times gravity. So 190 kilograms is the mass, and then the gravity is 9.8 meters per second squared. All right, so when you multiply those two together, they become a Newton force, and you get 1,860 newtons. So that's our load. All right, so 1,862, the effort is 350. So our mechanical advantage is the force of the load over the force of the effort is 5.32. Okay, and if mechanical advantage is equal to the velocity ratio, and this is only true when you have no friction, and it's an ideal machine, then also our velocity ratio must be the same. So that means that if I'm raising a load that's 5.32 times heavier, then I must put my effort 5.32 times as far away as the load from the fulcrum. So let's have a look at an example. As a simple one, if I put my effort 5.32 meters away from the fulcrum, then my load must be 1 meter away because it's 5.32 times more than that. I could also make the lever like this, 10.64 meters away, and then the load is 2 meters away. So if you divide the two, it's also equal to 5.32. So I hope that gives you a rough idea of ideal mechanical advantage. That is, when mechanical advantage is equal to the velocity ratio. That's when there's no friction involved. So therefore the efficiency is 100%.